In this video, we'll talk a little bit about the generalized idea and definition of what is a transformation in multiple dimensions. It's kind of like a change in variables from x to u in a u substitution, but say we have x and y and u and v, or x, y, z and u, v, w, or whatever. We'll kind of look at how that will happen. And in previous examples, we'd use the transformation from dv xyz typically into rho theta phi, and we had this kind of mystery rho squared sine phi that appeared and was necessary. So in the next couple of videos, we'll kind of talk about why is that the case. But kind of to set the stage, I like to think about in a u substitution, if we're trying to integrate a function of x with respect to x, sometimes that integral can't be really solved using our basic rules, but sometimes if we perform a substitution, in other words, we change x to some function of u, like x is equal to u squared or whatever, and then we consider, well, what is du, like 2u in that case, we can try to change our integral into a form that involves u, which is essentially just an application of the chain rule as a way of changing our integral into u to try to solve it. We'll think a little bit more about the geometry of that probably in the next video. But in general, a transformation, we could define it using capital T, which is a pretty common variable that's used to describe transformations in textbooks. Now, linear transformation is something that, for those of you who take linear algebra, will study more in detail with the use of matrices. There's kind of a fairly simple mathematical tactic for linear transformations, but in calculus, we're not necessarily going to be thinking only about linear transformations, because we want to think in general, what if we have any transformation where kind of, again, the idea is, say we have our variables x and y in our original double integral, and we want to change those to two new variables like x equal r cosine theta, y equal r sine theta in a polar transformation. So again, going from rectangular to polar is a type of transformation, as are cylindrical and spherical coordinates would be a three-dimensional transformation from xyz into three other variables. And again, u, v, w, just kind of generic variables, kind of like a u sub. We're doing a u, v sub or a u, v, w sub. And, you know, again, notice how these are exactly identical. X was defined to be based on, we didn't use uv, right? We used r theta, but because r theta have specific meaning, we did not want to just use generic variables. And with cylindrical and spherical, again, we have very specific meanings for those variables, which allow us to define the transformation. And again, sometimes we can think about inverse transformations, one-to-one, all other kind of relationships that are, it's like a functional map. But actually, in this example, let's just explore a sample transformation, because I think it can be helpful to think about what is going on in a multivariate transformation, because you can always kind of map it out using the equations. So say, for example, we had x defined to be u plus v and y to be defined as u squared minus v squared. It says, imagine we had a double integral across some kind of complicated region D of a function of x and y. We're thinking about it in rectangular coordinates, you know, integrating with respect to x and y, dx dy, or vice versa, whatever the case may be. Imagine, well, sometimes functions are very difficult to integrate, or we might not even be able to tactically do it using our algebra, because sometimes, right, integration just is hard. Often a substitution would be a tactic for trying to process or progress through that integral in a simpler manner. And similarly, sometimes if our region D is non-rectangular, sometimes a transformation or a change in variables will simplify that. And so in this problem, we're actually given a transformation defined by the equations x is equal to a function of u and v, u plus v, and y is also a function. This is what's called a nonlinear transformation, because these are involving squares, right? If it was no squares, just u's and v's only, it'd be a linear transformation, and it would actually be tactically much simpler. But in linear algebra, you will learn, for those of you who have to take Math 2033, you'll learn a little bit more about that process of using matrices to perform transformations. But when it's nonlinear, it gets a little bit more complicated, and sometimes creating a graph can help us sort of view and visualize what's going on with this transformation, much like we could think about u substitution changing parameters as well. Actually, before we get into this, let's look at This is something I usually will bring up in Calc 1 and Calc 2 when we're going through the process of U substitution, of how it really skews our graph. But even though we create a skew in our axes, we're not actually changing the final problem which we're trying to do. So for example, say we're considering this integral 4 minus 2x squared from 0 to 3, right? We'd be taking our parabola, which is this function, and integrating from 0 to 3 finds the area under the curve. And essentially, we could solve this by multiplying it all out, right? And just doing the math, finding the area underneath the curve based on the fundamental theorem. But in a U substitution, sometimes like changing the interior value to U can make this process simpler. So we're going to let U be the inside 4 minus 2x. When we change our variables, though, we have to also change our differential to match that change. And so if U was 4 minus 2x, well, du would be negative 2 with respect to x. And one tactic for changing our variables here is to solve for dx, because we have a dx. And in this case, if we divide both sides by negative 2, dx would be d over minus 2, right? But plugging all this in, we'd have our interior, which becomes u, our differential, which becomes du over minus 2, and we also need to change our boundaries to reflect this. This would be called a linear transformation because we're just changing our variables using a linear equation. When it's nonlinear, it's always a little harder. But again, if we plug in our boundaries, 0 would produce 4, 3 would produce negative 2, right? We get this integral, and essentially we can simplify our integral by our change in variables. And like, imagine this was a 5th power or a 20th power, right? The higher the power here, the more difficult integrating that function would become. But with a U substitution, it can tactically make life easier. And regardless, here's the important point I'm trying to make. The final question, the area underneath the curve is not changed, because in the original problem, we're solving an area from 0 to 3 of this parabola. When we make a substitution, we're actually skewing our value, right? U squared is a much more gradual, gentle parabola centered at a totally different point, right? Even the vertex changes. But the point is, if we properly change our boundaries and properly change our differential to correspond to U, all of it will still balance out, and the area of the corresponding change function from negative 2 to 4 will still produce the same answer. We're going to have 12 square units underneath these curves regardless of the change in variable. And how I tend to think of this is, in an integral that corresponds to x, all things must change, right? The inside, the function of x has to change to u, dx has to change to our du relationship, as well as our boundaries. All of those ideas apply still in Calculus 3 when we're thinking about nonlinear transformations. And creating a graph can kind of help us see how is our two-space region shifting when we're shifting our variables. And to start with, kind of how I'm thinking about this integral is kind of the goal here is to produce a simpler region where we're integrating with respect to u and v, where we're taking this on a rectangle of u and v. So in this case, it says find the image of r, but what's actually implied by the way this question is worded is these are u and v values, not x and y values. I know this is confusing because usually when we define a rectangle, it's corresponding to x and y. But in this case, it's kind of like in our UV region, it's much simpler. It's like a transformational rectangle. In our original units, though, it will not necessarily look like that. And the question is, what does the original region D kind of look like in terms of X and Y? We'll do that in a minute. And again, kind of our idea is our function we'd change to U and V based on plugging in this for x and y into our function. And lastly, there's also something that needs to be considered, which is called the Jacobian. But kind of like how we can't just directly change dx to du, we can't change dx dy to du dv because there's probably going to be some shifting factor. And that factor is what's called the Jacobian. We'll generalize this in a minute, but we'll kind of look at this in the example before we kind of get to that. So let's get into the question. So basically, our rectangle here is going from 0 to 3 on the u-axis, and it's going from 0 to 5 on the v-axis. So we just have a rectangular region here, and it can be kind of helpful to think about the boundaries of this region R, which looks kind of like that, as kind of moving around the corners of that region. Because if we change variables, it's kind of, our goal is to really think about how does how does u and v change into x and y? So what I'm going to do is, let's assume we start at the origin and we kind of move around this rectangle like so. Let's explore what actually happens to our x and y. Because in a nonlinear transformation, what happens is this rectangle will mold into some new shape. Now, if it's a linear transformation, it won't necessarily be a rectangle, but it won't kind of become curvy. Anyways, let's kind of start working on doing the transformation. I think you'll see what I'm talking about. But kind of the goal here is to take each of those points and convert them into x, y coordinates. Because, right, it's kind of like in a x to u substitution. We need to change u and v into x and y. In this case, we're kind of doing it the other way. But like say let's start at the origin specifically. So starting right over here, right? Then that's going to be the point 0, 0, of course. And so if we're thinking about our transformation, that would be, you know, u equals, sorry, my pen is acting up a little bit. Let's get this going. We would have x equals 0 plus 0 at the origin and y equals 0 minus 0. So turns out, well, in the transformation, we're actually still going to be starting at the origin as our translation of points. That won't always be the case, but makes it just easier to note, well, we're starting at the same point. And if we move along the x-axis along this rectangle here, well, let's focus on that specifically, because notice v would be fixed at 0, and x is going to move from 0 to 3, right? Because we're starting here, and we're essentially moving to 3. So let's write out what I just said. X is going to be, it's going to move up to 3 plus 0, and y would be 3 squared minus 0. Because again, v is 0 here, and u is essentially moving from 0 to 3. So that point would be 3, 9, right? And so essentially we're going to move all the way up to right here. But what we're noticing here is that if v is specifically 0, what we have is x equal to u and y equal to u squared. But this is actually just a parametric equation in general, because if v is fixated to be 0 along this axis, well, as we move along, right, it's just going to be controlled specifically by u. So if u is 1 at this point right here, we'd have 1, 1 would be our point right there. And then we're going to, as then we move to 2, we'd have 2, 4. So we're going to move up like this. And what we have is really just a parabola. So my point 3, 9 was poorly placed. Let's fix that. But essentially, we're moving up in the form of a parabola as we move along this axis. So this transforms to this. And our final point that we end up with is this corner, 3, 0, which changed to 3, 9 under the transformation. And that's kind of the point, is this transformation takes a rectangle and it kind of stretches it, skews it, it transforms it based on this parametric relationship. Now, if we focus on the next edge, let's speed this up just a little bit. Again, we're going to be starting at this point and moving. Now, in this case, u is going to be fixated to 3. Let me erase these scribbles so we can kind of keep track of this transformation as we go. But now u is fixated on 3, and we have v as what's changing. And so starting at our point over here, we're going to start at 3, 9 when v is 0. Then we're going to be moving up to v is 5. So kind of what I'm imagining is, as v increases, it's going to be moving, as v is 1, 2, 3, 4, we're going to have 4, 5, 6. So essentially, we're going to be moving to the right on the x-axis. And as v increases here, like say, let's start with just 1, right? We're going to have 4, 8. So we're going to be moving right here, moving down 1 in the v direction and 1 to the right. Now, if it's 2, we're going to have 5, 5. So we're going to be moving down here. And actually, what we're now going to have is a downward shaping parabola. It's going to be moving kind of like that. Let's plug in the next point, which would be, you guys can tell this is a little bit tedious to try to figure out how this all puts together. There are tools that can help you visualize transformations, which I want to show you. But the reason why I wanted to go through this example is visualizing what a transformation is actually doing and looks like is not easy, and it requires a lot of algebra understanding of these relationships between the equations. But, say we go to 3, then we're going to be at 6, 0. So we're going to be over here. And essentially, we're going to go all the way down. But we have this sort of parabolic shape moving down. And what can be nice is to think about, okay, what about when I finally get to this corner right here? We're going to be at 3, 5. So we're going to be at again, u is already plugged in. So at 5, we're going to be all the way over to 8. And 9 minus 25 is negative 16. So we're going to be way the heck down here by the time we get to the end. And so let's not be too accurate here because we're just trying to get a general understanding. But we kind of have this parabolic shape moving downwards like this. And what I'm expecting is the region to kind of move back this way. Technically, these regions can cross over and get all sorts of kind of complicated. But let's actually just plug in this point because we can be a little bit quicker with this. So at this point, we're going to have u equals 0, v equal 5. So we'd have 0, 5 and 0, negative 25 if we plug in that point. So as we move towards this region, again, we're going to end up at 5, minus 25. So that's going to be even further down here because this one was at negative 16. And the shape of this, I'm guessing it's going to be parabolic. But again, if we think about moving this way, we have v is fixated at 5 and x what's changing. So instead of writing a constant 0 in here, what we're going to have as well u and u squared. So essentially, we're starting here, moving here from those points. Like, let's say we wanted to do an intermittent point like 1 and 2. Well, we're going to have 6, negative 24. So it's going to just be 1 up. And then if we plug in 2, we're going to have 7, 21. So again, this is parabolic in a positive way rather than kind of the other way. And notice it kind of mirrors this shape almost precisely, as it kind of should, right? And then we can probably guess that this curve will map as we move back down this way, But just as a shortcut, let's just sort of sketch it out. And summarizing, this transformational region, is going to follow along. It's kind of helpful to put arrows along our parametric curves here to see, well, it's actually not really moving in the same direction whatsoever. And you can kind of guess that the inside of that rectangle will just be mapped to the inside of this new, whatever you want to call it. You could call it a transformed rectangle into our new region. And essentially, this is kind of what we could imagine is region D, because this is in terms of X and Y, right? Where if we're moving around a much more complex region, that's kind of the point of all this, is this integral might be very difficult to try to figure out how to define this region D in space. But if we provide a transformation, whether it's one way or another, can simplify that integral into a new point, into a new representation. But also, as we finish this example, kind of the final point here is, notice if we're thinking about the area of these regions, these regions are skewed from one another. They are not at all the same. So if we're changing dA from in terms of x and y down to du dv, what I would expect is du dv to be a fraction of x and y, because this is a lot bigger, right? If I'm trying to preserve this, I need to make sure that the preservation is intact. And actually, this is an idea that's kind of helpful to think about with linear transformations, which are even simpler. But this is straight from my linear algebra class, because the determinant of a matrix defined on a transformation can actually give us the area under a transformation. So let's actually pull up a GeoGebra document I made, which can kind of help us think about this. But essentially, if we're trying to perform a transformation, if we don't want to change our object at all, essentially what we'd be doing is letting u and v be equal to x and y directly with no other changes. And essentially, we're going to have exactly the same object. If we want to scale it in the x direction, it's kind of like we could think of it as a linear transformation. This would be, 3x or something like that. 3y would also scale it in another direction. And let's not worry too much about the specifics, but I think you can think about the idea, right? When we multiply by 1, 2, or 3, we're stretching our curve in a very specific direction. And in a linear transformation, what will happen is the area undergone by this transformation can be solved by a determinant. The reason why I'm talking about this is because if we want to think about how to perform a transformation that's nonlinear, or in calculus in general, it involves something called the Jacobian, which is the determinant of a set of partial derivatives, which we'll talk about in a minute. But additionally, you can also shear, kind of stretch it in different ways. But in linear transformations, you can do all sorts of different things within an object. And kind of the point I wanted to make here is, again, if for those of you who take linear algebra, you'll explore this a little bit further. The area of that transformation is defined essentially using the determinant of that matrix. And so if we look at the definition of the Jacobian, which, sorry, I'm moving around my slides too much, is right here. The Jacobian is defined to be a series of determinants based on partial derivatives. Again, which in the next video we'll practice with solving the Jacobian and thinking about how that would be. But sort of summarizing here, when we're trying to go from dA into du dv, there is some sort of scalar factor we need to take into account. Actually, it's not always a scalar, it involves the functions themselves. This video is getting long enough. In the next video, we'll get into the Jacobian.